Yes. Yes, it's exactly 1 minute past 5. I think we shall start, and the rest will find us in the way. So, good evening, everyone that has joined us this evening. We are very humbled and proud to present Miss Cindy Taff from SAGE Geosystems, and she's going to be giving us this webinar. And then I'll just go to the next slide. Just to remind the members here that a central theme for this year and for this board is sustainability, digital transformation, and energy transition. And before we begin anything, we would like to start with a simple safety moment. And this safety moment is about identity theft. And these are just some key tenets you can take to to prevent identity theft. Number one, check your credit report regularly. Never respond to unsolicited requests for personal information. Monitor your account statements for unauthorized transactions. Be aware of your privacy settings. Install firewalls and fire detection software, create complex passwords, and also write them because it's increasingly important. These days, so many accounts need passwords. Then destroy all documents containing your personal data. And now I would like to hand over to our publicity secretary to continue and to welcome the speaker. Thank you. Leen.
Hello, everyone. I'm so happy to be here with you today. This is our first webinar for this year, and we are so happy to welcome Cindy Taff, the CEO of SAGE Geosystems. We would like to have a small presentation or introduction about our speaker. Cindy Taff, as I mentioned, is the CEO of SAGE Geosystems. She has more than 36 years of oil field experience, most recently at Shell as Vice President of Unconventional Wells and Logistics over their global operations. She led her team to systematically reduce costs by 50% while improving safety performance as the exposure went up. Cindy holds a Bachelor of Science in Mechanical Engineering and is registered as professional engineer in Texas and Louisiana. Cindy, the floor is yours, please.
Thank you, Leen. Good afternoon, everybody. Thank you for the opportunity to present some background on geothermal energy and what SAGE is working on. Let me go ahead and, can I share, Gideon, my slide pack?
Yes, please, Cindy.
Right.
You are co-host, you can.
Thank you. All right. Hopefully you guys can see that. Gideon, can you see the slides?
Yes, we see.
Yes.
All
yes,
right,
we see them.
One thing I do not want to intend this to come across is as a sales brochure. I do want to point out, though, that these technologies, as well as others in geothermal, are being worked and they're not yet proven. So what I'm going to do is share our company's approach to the challenges that we're using to make geothermal cost competitive and commercial. One thing I also want to point out is geothermal is a natural segue into renewables for oil and gas companies because, like oil and gas, we drill into the ground to access a resource, but of course, in this case, it's heat rather than fossil fuels. And we just feel that there's a huge potential in geothermal that's been overlooked for years, and quite frankly, now is a great time to pursue it because there's such a worldwide focus and movement toward renewable energies. So before I get into the presentation, I just wanted to share what are the crucial pieces that need to come together for geothermal to be a competitive form of energy. So unfortunately, due to the high cost of geothermal, it is actually less than 1% of the utility electricity generation worldwide. So the challenges with geothermal are, one, effectively getting the heat from the rock into the working fluid, because we all know heat is a really bad conductor of heat. Second, it's getting that heat from the working fluid and efficiently converting it from electricity, from heat to electricity with the power plant. And then last but not least is the cost. So geothermal is at least double the cost of natural gas, wind and solar, but we also recognize natural gas prices are increasing. So we're all aware, this is just a kickoff slide, we're all aware that the world needs lots of clean, renewable energy. Our company is excited to be using our oil and gas skills because we think geothermal just may be the answer. And it will require leveraging the oil and gas industry to drill thousands of wells per year if we're successful. So just to give you a little bit of background on the benefits of geothermal. So it's got huge benefits as a renewable energy source. It's a baseload energy. It's available 365 days a year, whereas we know solar and wind are intermittent. They rely on, either the wind blowing or the sun shining. It actually has a small footprint. So, already the well is underground, but most of the power plant equipment can also be located under the ground. And I'll show you more pictures in the presentation. So it's mostly protected from weather. The other thing is it's everywhere beneath our feet. And it really can green the grid if we can, kind of crack the nut on the low to mid enthalpy geothermal. And then regarding the modularity that we have listed, what we're estimating with our technologies is we should be able to generate about 3 megawatts from 1 or 2 wells, depending on the design. So for like a 50 megawatt commercial application, we'll drill a 10 to 15 well pad. And in talking with the turbine company that we're working with, we would not need one big 50 megawatt turbine. We could get away with turbines on each of the wells. So you naturally have redundancy in the system.
Hey, Cindy, can you switch to presenter mode? Right now we're seeing a big PowerPoint.
No problem. Thank you for asking that. Let me know. It gets weird on my side. Did that work?
No, we're still seeing the
No, not yet.
Okay. Does that help?
No.
No. Okay.
This PowerPoint now, can you just do a full screen?
It's going like into a full screen on a different screen. Let me see if I can stop sharing and reshare. Sorry about that.
Oh, it's okay. Take your time.
Perfect. Okay. All right. So to provide a little background on the type of geothermal systems, we all need to think about the subsurface environment. So the geology drives the type of geothermal system that can be used. So most of us are used to the conventional hydrothermal systems, which are installed in areas where you see steam coming out of the ground. So near volcanoes or the Ring of Fire. So you think about Iceland, you think about Northern California. So these systems are relying on the hot aquifers of the water or steam to bring the Earth's heat from subsurface to the surface. It's very, very efficient because it brings the heat, brings a lot of it. Unfortunately, these higher temperature reservoirs in this crystalline rock make up only 2% of the geothermal resources around the world. Again, only 2%. So most of the geothermal resources are contained in what we call hot dry rock, which you've seen on the slide, meaning rocks that don't naturally flow water. In these rocks, you have to create an artificial reservoir in which you pump water or another working fluid to harvest the heat from the earth and then circulate it back to the surface to get the heat out of the working fluid. You guys may have seen these systems before. They're called EGS or enhanced geothermal systems.
Yes.
Okay. did that go to the next slide? Maybe not. Okay, there we go. Sorry about that. So again, the challenges for geothermal include the inability to get sufficient heat from the rock, as the rock's a poor thermal conductor, the low efficiency of the overall system to convert that heat to electricity, and then the high upfront cost of basically the well and the power plant. So SAGE Geosystems, we're targeting a lower temperature range, so 150 to about 250 degrees C. And it's much lower than traditional geothermal. And we're targeting sedimentary rock. And so why is that? It's because we want to be able to put geothermal wells just about anywhere in the world, and not just in the challenging subsurface locations like near a volcano or the Ring of Fire. And it also allows us to use off-the-shelf oil and gas equipment, people, and technologies. So we're very excited about that. It is a nut that needs to be cracked, though. The other thing that we feel critical to address in these systems is having an integrated system approach, which covers both the power plant and the well. So it's something that's been used in the oil and gas industry for years for complex plays like deep water. So basically, you can't just optimize the well and you can't just optimize the power plant. You have to optimize both, and you have to optimize them as a system. And you'll see more about our approach on that integrated system as I go through the presentation. We also recognize that, as I walk through the geology, there's not a single optimum geothermal design for all applications and all subsurface environments. So we've got multiple approaches and technologies to address the different subsurface environments, whether it's hot, dry rock or the hydrothermal type of well environment. And then last but not least, we feel it's really important to have a system level modeling tool, which allows you to basically input the well characteristics, the working fluid characteristics, the power plant conversion. It's kind of a thermodynamic model, and it'll output the estimated megawatts of electricity that you can generate. So we've got an in-house tool that we're using called GeoTwin, but we do think it's a critical part of the process. So by lowering or by targeting the lower subsurface temperatures, we, again, feel like we can develop really significant geothermal resources that are available in sedimentary rock at temperatures of 100 to 250 degrees C, using off-the-shelf oil and gas know-how. And as seen in these maps, you can actually access these temperatures at depths of about 3 to 6 kilometers around the world, which is very accessible to current drilling technologies, and so off-the-shelf technologies. So SAGE, we're located in Houston, Texas. We're currently focused on the area along the Gulf of Mexico, in the state of Texas and in the state of Louisiana, as shown on this map by the red stars. So it's mainly geopressured formations. And we feel like, and there's been studies that show that there's huge geothermal potential here, again, in the lower temperature range. So the United States Department of Energy has actually spent a lot of money dating back to the 1970s to evaluate the geothermal potential in these areas. And they feel like the Texas and Louisiana Gulf Coast are, again, a huge area of potential. They think just along the Gulf Coast in these two states, there's about 5 gigawatts of geothermal energy potential. So currently, the worldwide geothermal electricity generation is about 16 or 17 gigawatts. So it's about a third of the current geothermal power capacity around the world. And this is with technology that's like 25 years old. You see on the slide on the right-hand side, the Department of Energy actually drilled a well in 1989 called the Pleasant Bayou well, and it was successful. It made about 0.5 megawatt of power from the thermal energy, and then about 1 megawatt of power from the natural gas, which we're not targeting. We're targeting the geothermal energy. But it was also, again, in 1989, so with very old technology. This well was a hydrothermal type of well, so it was completed in a formation that produced a lot of water, and it proved successful. The reason the well was shut in, and again 1989, is because oil and gas prices were just so low, and also there just wasn't the focus that we have now on renewable energy. So we really just think this is a perfect time to be in geothermal. So to share some of the technologies we're working on the left-hand side is a technology that we're calling heat flood. So heat flood is basically a typical hydrothermal well design. It is modeled after that DOE Pleasant Bayou well that was drilled in 1989. It relies on the formation to produce hot water, but in, again, the lower temperature range, so 100 to 250 degrees C. And again, we're targeting hot aquifers with high flow rates, so preferably 10,000 barrels of water per day or greater. And that can be either from natural permeability or after being stimulated. Now, the other two well designs on the right-hand side, they target the hot, dry rock. So HeatRoot is our single well EGS system that uses a downward oriented fracking technology to basically create that artificial reservoir that I mentioned, and which you would then use to circulate water or another working fluid through to harvest the heat and then bring it to the surface. I'll show you some pictures later, but we're actually in the middle of a field test right now in South Texas in an old abandoned exploration gas well. And we're testing this single well EGS technology as we speak. We'll be fracking in February and circulating in kind of mid to late February. So we should have results by the end of February. And then the last one on the right, Heat Loop. Heat Loop is a alternative hot dry rock design using multiple well bores, but again, it uses downhole circulation through laterals that are connected by either fractures or other lateral well bores. So again, it's another hot dry rock design. So now what I'd like to do is share with you what we're doing to improve the power plant performance. So again, we talked about the overall system, not only the wells, but the power plant. So we see a huge opportunity in using supercritical CO2 as the working fluid, and combined with the proprietary CO2 turbine that we're building right now, and that uses the Brayton cycle instead of the organic Rankine cycle. We feel like this is going to allow us to double the utilization efficiency or the output of the turbine in converting heat to electricity, and also cut the cost in half. So we're working with a company called Southwest Research Institute in San Antonio. We're in the detailed design phase of this turbine, and we should be bench testing it in kind of the May-June time frame. So SWRI, or Southwest Research Institute, they already have experience building these CO2 turbines, and they've built them, designed and built them for higher temperature applications for concentrated solar. And our turbine, of course, will be much lower temperature range. So again, around 200 to 300 C. And it's for us to target the low to mid enthalpy. So in the picture on this slide, you can see the turbine blades. There's one in the background. That's a turbine blade from a steam turbine that uses the organic Rankine cycle. And then the turbine that the two gentlemen are holding is actually that concentrated solar CO2 turbine that Southwest Research Institute built. It's much smaller, so therefore it's going to cost a lot less. So our particular turbine will have turbine blades about this size, 8 inches in diameter and 8 inches in length, and the overall turbine will weigh only about 300 pounds. So just one other thing I want to mention is that the Department of Energy, you'll see a common thread here. We're kind of following the Department of Energy, but they're spending a lot of money on this CO2 Brayton cycle technology as they also see huge benefits. So again, we're hoping that this CO2 technology will double our output efficiency of converting heat to electricity, as well as half the cost. And we should have our first test results by June of this year. So I talked a little bit about our commercial installations in the Gulf of Mexico area. One of them is in very South Texas. You can see by this red dot on the map. It is with the city of McAllen. So what they want to do is install a 3 megawatt microgrid, and a microgrid is a grid that would be dedicated just to their facilities and would not be hooked up to the utility grid. So they want it to run their water treatment facilities, and they don't want to be dependent on the grid. So it's very interesting because the city of McAllen actually sits directly over a geopressured gas field that's called McAllen FAR, which makes geothermal just an ideal renewable energy source for them. The other things that they're interested in is water desalination. So when you have a what we call a heat flood type of well design, and you're actually producing this formation water is actually pretty low in total dissolved solids, so it makes it perfect to desalinate for either agricultural or community use. And so we're very interested in one of our next steps to be looking at water desalination, because we've got a lot of drought-stricken areas, not only in the US, but around the world. And we think that by desalinating the water, we can solve some of those issues. The other thing we have been looking at, but it's not a big focus area, is a lot of this produced water at these greater depths and temperatures actually have minerals that are of great value. So lithium, you guys have heard all of the lithium shortages due to the batteries. So lithium is of interest, and there's a lot of companies being formed out there that are perfecting the technology to actually extract lithium from water, which is actually a lot cleaner method of mining lithium than some of the rock mining that is being done around the world. We're also partnering with the University of Texas. They have a group called the Bureau of Economic Geology, and we're performing a feasibility study for the United States Air Force to install a geothermal, again, microgrid on their military base just outside of Houston here called Ellington. So we're evaluating the installation of a 3 megawatt microgrid. So again, our technology, we're estimating we should get 3 megawatts from a single well. And then if we're successful at Ellington, the military is quite interested in leveraging this technology for some of their other bases. So as you guys can imagine, critical infrastructure like military bases or hospitals or data centers, geothermal is just a perfect application because it gets them off the grid. And that means potential power grid disruptions due to weather, or, when you're thinking about military, there could be physical attacks. It actually divorces them from these power grid disruptions. So it's really seen as a what the military calls a very hardened electrical grid. I did want to show some pictures from the heat root field test that we're doing. I mentioned in South Texas in this abandoned gas exploration well. So what we did in the first picture, you'll see that the well was abandoned. It was covered with dirt. We had to actually go out there with GPS and find it. We excavated the casing stubs back. And then in the second picture, we reinstalled the wellhead. And then the third picture, it shows the whipstock that we're using to drill laterals. And then you have to excuse our kind of, the visual to the very right. That is a depiction of our heat root technology. So what we're doing is we're drilling laterals about 350 feet apart from each other. And then we're going to be fracking down from the top laterals to the bottom in order to connect them and create these penny-shaped fracks that you see in the picture. We're only drilling 4 laterals. This is showing 8. So it'll be half of what we've got in this picture here. But what we're trying to do is prove that we can connect these laterals, and then we'll be circulating through them and seeing if the amount of heat that we are harvesting goes up from just circulating in the wellbore. So another thing I wanted to share is, I talked about the economic or the cost challenges with geothermal. So, we've got a performance path to be competitive with natural gas, wind, and solar. So these are the charts on the left is what we call a waterfall chart. It's the same type of charts that are used in the oil and gas industry. So, on our first one-off installation, we are going to be more costly, as all one-off projects are. And then we estimate, so it'll be about $5 million per megawatt, which equates to about 5 cents per kilowatt if you want to think about your own electricity cost at home. As we standardize our well design and our power plant design, we want to drill multi-well pads. We want to move into what we call manufacturing mode in the oil and gas industry. So we're targeting that in 3 to 5 years, we should be able to get those costs down to about $3 million per megawatt, which is not unusual. Those kind of learning curves are very typical in the oil and gas industry. We had those in deep water. We had those in the unconventional shales. And so if we're able to do that, we will definitely be competitive with solar, wind, and natural gas. So this is my last slide, and then we'll go to questions. I did want to share, just out of interest for you guys, who our investors are, because it gives you an idea of who is interested in advancing geothermal. So our 2 investors currently are Vera and Neighbors. So if you guys have heard of TED Talks, Vera was founded by Chris Anderson. Chris Anderson owns TED Talks, or is the curator of TED Talks. He's a self-made British billionaire, quite frankly, and he wants to do good with his money, and he wants to make an impact on greenhouse gas emissions. So he's been investing in geothermal and in nuclear, and quite frankly, he's been just exceptional to work with. He's very supportive, but at the same time challenges us, which is great. And then Neighbors, you guys being the SPE, hopefully you've heard of Neighbors. Neighbors is one of the world's largest oil and gas contractors. They have operations around the world. And why are they interested? Because they also believe geothermal is very promising as a renewable energy because it's base load, available 24 hours a day, 7 days a week, but also because it's a natural workforce transition option for their oil and gas professionals as well as their equipment. So again, there's a significant overlap in skills and equipment between what is needed for the oil and gas industry and what is needed for the geothermal energy, So Gideon, with that, I will pause and happy to take any questions that you guys may have.
Thank you so much. Now we'll move to the Q&A session. Okay, we have 2 questions in the chat already. And after those questions, whoever needs to ask something, please feel free to unmute yourselves to increase the interaction. Okay, the first question is, how do you quantify the fracture dimension versus heat flow in the heat route example?
So, I'm sorry, is this in the chat? So I can look at it as well? Yeah, okay. How do I quantify, say again?
How do you quantify the fracture dimension versus heat flow in the heat route example?
Yeah, it's a good question. We're actually in our GeoTwin modeling tool. We are working currently with a consultant to put the fracture, not only the fracture dimensions in the modeling tool, but we've also found that the permeability of the rock is important. Now, why is that? It's because you want, what we're finding is you want that working fluid to be in the matrix of the rock, because the effectiveness of being able to harvest the heat from the rock will be increased. So I will not try to answer how we quantify. All I can say is that our GeoTwin modeling tool is currently being revised by some very smart people that know how to do this modeling work. And after they're done with that, then I can probably answer that question better. But it is being worked right now, and it should be what the heat root test well will allow us to do is also calibrate that GeoTwin modeling tool with the fractures that we're putting in the ground. So it's a great question, and I would say that we're working on it, and hopefully our modeling tool will be quite accurate by the end of our test.
Okay, thank you so much. The second question is somehow long, if you prefer to open the chat.
You bet. Okay.
Okay, it starts with additionally, how does the SAGE handle the heat loop system?
Yeah, in terms of knowing at what points of fracture communication. Yeah, I'm not sure what that is referring to. What we're doing at the point of fracture communication that's sufficient. Yeah. What we're trying to do is very similar to the traditional EGS that is being done in other locations for geothermal, quite frankly, in crystalline rock typically. So for heat loop, we're trying, what our reflection is that heat root, which is a single well EGS, may not be sufficient to give us enough aerial extent for the working fluid to have that contact with the rock to be able to harvest enough heat to be commercial. It will harvest heat, but whether it'll harvest enough heat to be commercial. And so what we're going to have to do, and to be honest with you, heat root and heat loop are both unproven technologies. So when we get to the point of testing heat loop, which we suspect will be kind of the late this year after we get the results of the heat root test, or early next year, then it will be a matter of modeling the results that we got from heat root and how much aerial extent we estimated that we got in that well, and then designing our heat loop wells to ensure that we've got the length of the radials or the well bores if we're going to be drilling 2 well bores, and then that fracture connection. We'll use the calibrated modeling that we got from the heat root field test to be able to inform what that heat loop design is going to look like. And I'm hoping that answered the question. I know it was kind of a little bit around beating around the bush to get there, but I did want to say the heat root field test that we're currently doing will inform what the heat loop design will look like. Okay, so yeah, the next question, how is isolation dealt with at high temperatures during geothermal stimulation? So just recall, we are working at bottom hole temperatures and bottom hole pressures that the oil and gas industry work with at all the time. So we'll use some of the same tools, in the unconventional space where I worked at Shell for years. We use some of the same plugs and tools that were used in the unconventional shales for, if say we're drilling a lateral and we want to frac multi fracs along that lateral, we'll use the same type of plugs because it's the same bottom hole temperatures. We're not going to the ultra high bottom hole temperatures that the traditional geothermal wells will go to. So that's again why we're trying to stay within the temperature range that we are targeting, because we want to be able to use off-the-shelf oil and gas technologies. Now, with that being said, we're closely following the newer technologies that are being used for the crystalline rock and the higher temperatures, and we will be fast followers. But we don't want to be on the leading edge of that. We want to be more fast followers. So I'll just give you an example. Usually in crystalline rock, so igneous rock, your penetration rate during drilling may be 60 foot per day. Well, NOV has come out with a new bit that was tested in the Forge project here in the US. And they demonstrated that they could get 60 foot per hour, which is very good. It's very much like sedimentary rock, which is softer. So these penetration rates were very high. So as those technologies advance, we will again, start looking at igneous rock and crystalline rock. But for now, we want to kind of stay in the sedimentary rock and the lower temperature range where the off-the-shelf oil and gas technologies can be used. So yes, you can definitely have my contact information, Leen or Gideon. I can send that to you.
Yes, of course.
Yeah, and I'm happy to meet with anybody one-on-one. I'm excited that you guys are interested in renewables. I'm excited that you guys are interested in geothermal. We recognize that there's a lot of education that needs to be done on geothermal. And, let me just reflect another thing is the geothermal that we're working on, I heard somebody call it new geothermal, which kind of made me smile, but it is. It's the lower temperature part of geothermal has not been around very long. The high temperature, Iceland, where you have the steam coming out of the ground, it's been around for 25 or 30 years. So it's been around a long time, and it's a very proven technology. But we're hoping that, between the EGS systems that other geothermal companies are working and the low temperature that, we're working as well as other geothermal companies, we're hoping that as an industry, we can crack this nut and really make geothermal, available in more applications and more parts around the world. Yeah, so CO2 and water are two working fluids for geothermal. Are there others? Yes, like nanofluids is interesting. I'm not sure if nanofluids have been used, but other types of fluids like isobutane have been used, just fluids that have more favorable thermodynamic properties. And what I do want to say is our CO2 is contained in a closed loop system. It doesn't interface with the rock. We have, what we're doing is the water will harvest heat from the rock, and then the heat from the water is transferred to the CO2, and the CO2 is what runs our turbine. So it's definitely a closed loop system, kind of like the air conditioning system in a lot of residentials. But yes, nanofluids is interesting. I'm glad you asked that question. I have not seen nanofluids being used. The efficiency of the supercritical CO2 power plant in San Antonio. We're bench testing it in San Antonio, and we expect to see a 20 to 25% utilization efficiency, and that is compared to the organic Rankine cycle efficiency, which is less than 10%. So that will be our measure of success, is that we can at least double the ORC efficiency. Yeah, so geothermal plants claim to have a small footprint compared to wind and solar. With SAGE's advanced technology, what is the land size for, say, a 15 megawatt plant? So 15 megawatt plant, we would estimate would be, say, a 5-well pad. We can drill wells in the oil and gas industry 5 to 8 feet apart. So the well footprint's very small. You guys saw the turbine. So if we put one turbine per well, you would put that turbine in the gearbox basically in a 20-foot shipping container per well. So that's very small. The big part of the footprint for geothermal is cooling. So if we had a 15 megawatt power plant and say we were in South Texas, which is very hot, I would say that it's going to be less than an acre, and most of that footprint would be the cooling. Now, what's interesting, if you guys think about it, is offshore. So if we went offshore and say we repurposed a offshore platform, what we have naturally right there is the seawater, and the seawater could be our cooling mechanism, which means then your footprint would be obviously the well, which is downhole, the turbine and the gearbox and generator, which is on surface. And then you would use the seawater to cool the CO2, which would be very efficient and would mean our parasitic load would be quite low. So, but good question. So we're expecting for a 50 megawatt power plant, the footprint would be less than an acre. Yeah, what are some of the current constraints for geothermal taking center stage? It's a great question, and I think it's education. I think, that's why we get excited when, student chapters of SPE ask us to present, because we want to get the word out there. I think it's education, but I also think it's that we need to prove this new geothermal technology. So again, geothermal has been around for 25 years, but it is the very traditional hydrothermal, which is around volcanoes, and it only represents 2% of the resources globally. If we and some of the other geothermal companies like Ever and Greenfire and Deep and Fervo are able to prove their technologies, we think that geothermal will be much more prevalent, and then it'll start showing up on some of these renewable energy projections that typically don't have a big slice of the pie given to geothermal. So that's a great question. Does the use of CO2 in the Brayton cycle overcome the loss of energy during the use of two fluids, as heat by definition is transfer of energy? Great question. So you're exactly right. So in the organic Rankine cycle, a lot of times the water is changing phases, which means that you are losing energy. In our Brayton cycle, the CO2 does not change phases. So that's one way that we conserve energy. The Brayton cycle also uses a pressure component in it to help spin the turbine. So that's another way that we use energy that is naturally coming out of the well. The reason why those two reasons, we're staying in supercritical, and we've got a pressure component in the Brayton cycle, are the reasons why we think the Brayton cycle will produce twice or double the utilization efficiency. So yes, we think the Brayton cycle will overcome the use of two fluids. It's a good question, because you're exactly right. You do lose energy when you are transferring heat from one fluid to another. The other thing I wanted to mention too is you guys didn't hear me talk about district heating. It's not that we're not focused on district heating, or not that we don't acknowledge it. We think district heating is a great way to use geothermal energy, but our investors they're very interested in generating electricity, because electricity is more usable, it's more flexible in application, and so that would be that's another way that you lose energy, is when you just convert the heat to electricity rather than just using the heat as heat in district heating. But we are more focused on generating electricity than we are using it for district heating. So I will pause there, Leen, and see if there's any more questions.
Thank you so much. Thank you everyone for your questions. Okay, we have another one. Okay. Thank you so much all for your questions. And thank you, Cindy, for this very informative presentation about the geothermal energy. And now I hand it over to Gideon, our president, to finalize the webinar.
Yes, thank you very much, Cindy, for the wonderful presentation about geothermal energy. Actually, I'll share with you that the IFP student chapter is planning to travel to Iceland to continue to learn more about geothermal energy, because we believe that it's the part of the energies of the future, and it will provide a higher capacity for companies and industries to be able to continue in light of the energy transition. And then again, obviously, it is, as you hinted on in the beginning, that geothermal energy is already banking on existing technologies, using turbines and the drilling for oil. So I think we have a range of technologies already ready that just need to be put together to do this. So thank you so much, Cindy. Once again, we were honored and very profoundly humbled to have you this evening. And we hope to interact with you further on other occasions. Yes, just to present finally, this is a final slide about what we do with the SPE and the IFP chapter. Of course, we have conferences and webinars such as these. We participate in events. We do company visits, social events. We have a very big diversity and inclusion committee, and then Petro contest, networking, and other things. So hopefully through the Petro Bowl, maybe our team will be in Houston sometime this year in October during the ATCE, and maybe we'll get a chance to meet again. Thank you once again, and I would like to call this meeting to a close.
But before doing so, can we have a group photo together? So if everyone can switch on their cameras so that we have a photo together. Okay, great.
Thank you.
1 minute. Cameras are being switched on. Okay. Let's do this. Okay. Thank you so much. Thank you so much.
Thank you. I was honored. Thank you for having me.
It was our honor.
Can you share this photo to the mail?
Of course. And we will post it on our social media platforms so everybody will have access to it.
Okay. Thank you.
Thank you. Thank you so much for attending. Thank you. So, bye-bye.